Hi, I'm Mohammed Abdallah, a chemist in Delta Steel Mill Company, the spectroscopic laboratory. Today I'm going to make a presentation on how to use optical emission spectroscopy to determine quantitative and qualitative measurements for solid samples based on iron. First thing you should know is the theory of atomic spectroscopy, then the instrument components and how we introduce our samples. So what is atomic spectroscopy and how it differs from molecular spectroscopy? To get to the accurate answer, we should talk about electromagnetic radiation and its interaction with matter. We all know the electromagnetic spectrum. It spreads over a vast values of wavelength and frequencies. Imagine that an electromagnetic visible beam, or UV light incident to a piece of glass or a cuvette contains a particular solution. We should expect that with UV light makes the incident beam I node differ from the transmitted beam I1, there will be an absent frequencies in the transmitted light. And this will be due to the absorbance of specific light by atoms and molecules in the samples. In fact, Albert Einstein and Planck's experiment about photoelectric effect stated the first thoughts about quantum mechanics. Photoelectric effect is the emission of electrons when light shines on a material. They noticed that atoms emits and absorb electromagnetic waves at specific values. Albert Einstein measured the Planck constant and denoted that energy equals Planck's constant multiplied by mu. That means that the energy absorbed or emitted by an atom depends only on specific energy because Planck constant can't change. It means also that these energies are quantized. For example, iron atom in gaseous state after appropriate excitation with energy, by heat, or electric arc, will emit thousands of electromagnetic frequencies. All this frequencies is at specific values and don't differ for any iron atoms, but of course differ from that of, let's say, copper or grass or oxygen. Scientists call this frequencies as line spectra because it was appearing as lines on a photographic plates. The simplest way to measure these lines is to use any dispersive element, like a prism or a differential grating in which it disperse the light emitted from an excited element to its component, and these frequencies or light will be printed on a photographic plate like an image. These lines called the spectrum of that specific element. Scientists had taken all the spectrum of all element in the periodic table. All elements has a specific spectrum consists of black lines on colored background, and this is called absorbance spectrum, or colored lines in black background if it is emission spectrum. We can make a qualitative measurements for any samples contain a large number of elements, by analyzing the resulting spectrum, to know if our sample contain iron elements or not, gold or not. We don't need to measure all iron line spectra, we choose only some characteristic line for detection. Quantitative measurement can be done according to Beer's law. He noticed that the amount of absorbed light proportionate with the concentration exponentially by this relationship. Log I naught divided on I1 equals epsilon Lc equals absorbance, A. Where epsilon is the molar absorptivity for this substance, and it is characteristic for this substance, and L is the bath length of the cuvette and C is the concentration. This relationship gives us the way to measure concentration, as absorbance depends only on concentration, while L and epsilons remains constant. That means the relation between A and C is linear, and we usually call this curve calibration curve. Molecular spectrum is very complicated because molecule don't possess transition energies of electrons only. It have rotational and vibrational energies too. So its spectrum doesn't appear as line but a large number of lines combine to make a continuous curve. See this figure. We will focus only on atomic spectroscopy and its application, so we can divide spectroscopic analysis to atomic and molecular spectroscopy, or absorption and emission spectroscopy. In fact, there is a large number of spectroscopic techniques. It depends on the range of frequencies used and the related atomic and molecular properties. In fact, there is a large number of spectroscopic techniques. It depends on the range of frequencies used and the related atomic and molecular properties affected by these range. Such as nuclei spin in NMR spectroscopy, it uses radio frequency to affect the spin of a nuclei, rotation of molecules and orbitals in ultraviolet spectroscopy, vibration of molecules in infrared spectroscopy. There is a large number of spectroscopic techniques, for example, acoustic resonance spectroscopy, Auger electron spectroscopy, coherent anti-Stokes-Raman spectroscopy, cold vapor atomic fluorescence spectroscopy, deep-level transient spectroscopy, dual polarization interferometry, electron paramagnetic resonance spectroscopy, force spectroscopy, Fourier transform spectroscopy, Fourier transform infrared spectroscopy, hadron spectroscopy. Spectroscopic instruments come with various size to fit its wide applications, from tiny one to huge one. You can imagine the telescope of Hubble as an spectroscopic instrument. Some ways we use spectroscopy in a practical manner include: in astronomy, we can use the unique spectra to identify the chemical makeup of objects in space. We can also use it to identify properties about space objects, chiefly their temperature, as well as their velocity. It has applications in metabolite screening and for analyzing and improving the structure of drugs. We can use it to measure sampled chemicals or nanoparticles through their mass-to-charge ratio, using a mass spectrometer. It was a surprise that Albert Einstein won the Nobel Prize, on his explanation of photoelectric effect, not for his theory about relativity. Science may concern more about facts and things we can measure. The quantum theory emerged to explain more about atoms, and the micro-scale universe. After decades, the spectroscopic techniques was a result of quantum and atomic physics studies. It was developing during the last century, and Nobel Prize awarded to a lot of people related to spectroscopic techniques more than the aspects of quantum chemistry. So we will focus here on atomic spectroscopy. Now, I can tell what is a spectrometer. A spectrometer is a scientific instrument used to separate and measure spectral components of a physical phenomenon. There is general description for almost spectrometers. Instrument principle. An OES instrument is therefore composed of the following parts illustrated in the figure. 1. An excitation source, which allows the ablation of material from the sample and produces the discharge plasma where all excitation and radiative de-excitation processes of interest occur. 2. A dispersion device, which separate the different wavelengths to produce a spectrum. 3. Readout electronics, which allows acquisition of the spectrum wavelengths. 4. A computer that processes the measurements and controls the instrument. I will illustrate these components in detail, but you should remind that our main issue is optical emission spectroscopy, OES, especially for analyzing steel alloys that our company producing. So let's begin with our samples, and how we get it excited. This is the common samples in our mill, and chemists should recognize it. There is also another samples with different shapes and concentrations. The optical emission spectroscopy analysis is based on the following physical principles. An high-energy source is used in order to generate a discharge between the surface of a conductive sample and an electrode. This discharge is responsible for ablation of element particles from the sample, followed by excitation of the ablated element species in the plasma. The plasma temperature is sufficiently high that a part of the atoms are ionized, and both atoms and ions are excited, i.e. electrons are promoted to higher energy levels. One of the de-excitation mechanism is the radiative one that causes emission of light at wavelengths characteristic of the emitting element. So our samples is always solid, and that makes accuracy of spectroscopic analysis drops to 1 to 10 part per million only. Liquid samples can be detected to parts per billion, or even trillion, but for steel making 1 part per million is enough to achieve our product quality. The plasma consists of high temperature atoms, ions, particles, electrons, etc. We use tungsten electrode with 2000 volt as a source of excitation. This will promote electrons in the plasma, makes single atoms of all elements, emits its characteristic line spectra. We detect it and obtain our quantitative and qualitative analysis. After the excitation of elements in plasma, the electromagnetic radiation, in which in this case located in ultraviolet region, electromagnetic radiation should be resolved to its wavelengths or frequency components. We use monochromator with differential grading for that purpose, As you see, the beam at the entrance slit contains all wavelength, combined in one beam, and at the exit slit the beam was dispersed. We can make the differential grading move to make all spectral lines pass through the exit slit to the detector, which gives the values of these frequencies and the intensities of the lines. Notice that all electromagnetic radiation is not visible to the eye, just the very little range of visible region, so we don't usually see anything during spectroscopic analysis. The detector should be sensitive for spectra or the specific frequencies, which we are measuring. There is two common types of detectors, charged couple detector, or CCD, it depends on photovoltaic cells, and it resemble your Android camera. It is very fast but expensive and easy to get damaged. The other one is photomultiplier tube, in which a photon hits an anode plat ejecting one electron, and the electron hits a series of anodes ejecting more electrons, reach to cathode and measured as electric current, represent the frequency or the wavelength. Every element should have its photomultiplier channel to make able to detect. The last thing is electronics, and the displaying device such as PC screen. You can see here a practical run showing the concentrations of element by weight %. Notice the detection of small concentration of some elements. This was a very short presentation, and my first presentation indeed. Thanks a lot. Goodbye.